Let's get started. Here we go. So we've got some announcements. Lots of announcements. Here we go. We need people for interviews, $25 an interview. So we'll just put some questions about Calc 2 in front of you and just listen to your thinking, and you'll solve the problems, and we'll take notes, and then about an hour, $25, and then there may be, for some, it may be more than one interview. So go to this website and then read carefully. All the information is there, and how to set that up. Okay, so please respond if you're interested in that. Okay, recitation today is, I forgot to talk about this Monday, but recitation's Monday, and today we're all optional and open to everyone, just study session, getting ready for the exam, doing homework. So what is the room number for recitation today? Who knows that? Nice and loud? 113. Wexler? Wexler 113 at what time? 11:50. Wexler 115. Is that right? Is that what you said? I'm so confused. The room number is 113 and the time is 11:50. Okay. So anyone's welcome to go to that. Let's see. Ben will be there to answer questions, facilitate study session, and help you with your homework and studying for the test. So all welcome to go. There's no recitation on Friday. No recitation on Friday. We have the exam on Friday. So it's the same exact procedure as last time. I sent an email out about people who have conflicts or reschedule. I've only gotten 2 replies to that. If you have a conflict, you cannot change. You can't make 90 minutes work. What was it before? Between 9 and 11:30. If you can't get there for 90 minutes during that time, then you need to respond to that email today. We need to make alternate arrangements. I've only heard from 2 people. So if I don't hear from you, we'll expect you at the art building sometime between 9 and 10, starting between 9 and 10 for 90 minutes. What else? There is the stuff that we do today is on the exam, and there will be a short web work so you can practice that stuff along with the examples we do in class. Okay, let's look at so I've put up lots of materials in exam prep. So there are lots of these resources are focused on the recent stuff, finding accumulation functions in closed form, right? Taking open form accumulation functions, finding their closed forms. But that's not indicative of the proportion of the test that's that. Okay, so let's look at the review outline. Exam 2, Concepts and Skills. So I think I mentioned last week that signed and unsigned area, volumes of revolution is part of this exam. You won't be building those from scratch. It's not going to be the same, but you do have to know how to identify those rate functions, know what those rate functions are for signed and unsigned volume, and the 2 different kinds of volumes of revolution that we did. You need to know those rate functions, and then the subsequent accumulation functions for those. Be able to identify them, know the geometry of it, okay? So make sure you read through this carefully, all these bullet points, and you're still up to speed on area and volume. And then we have arc length and surface area, which is mostly new. Same kind of thing, but here, this might be a little more extensive on the test, because it's the new stuff. Physics applications. All right, so those are the 3 topics that were like applications of accumulation functions in open form, right? In open form. To study for this, you're going to be looking at examples in the book, examples in the homework, and the lectures, the lecture videos, okay? I don't have an extensive list of practice problems, so it's up to you to dig into the text, the homework and go back to the class examples. It will not deviate from that. So the exam will not deviate from what we emphasized in class and the homework that you did. So you won't remember, you're not going to remember those homework problems. Go back and do them again. Okay? Going back and do them again. That's great practice. And then in terms of this new stuff, defining closed forms techniques, lots of practice there. So I've got, there's a whole worksheet. There's a website with more. And then, so that's it. So there's lots of practice here in the exam prep post for the new stuff. These techniques for finding closed form accumulation functions. But all the conceptual stuff, the building the accumulation functions for all those applications of geometry and physics, you're going to have to dig into the written homework, the book, and the lecture examples. Yes, please.
Will you post the solutions to the homework problem as you did the last one?
I wasn't planning on. For which now?
For like this exam. I just like the recent homework problems.
The recent homework problems. Oh, in the book?
Yes.
Yes, I will. I think it's chapter 8. Is it the physics stuff?
So,
yeah, I will post a something with solutions from the chapter 8 homework. Yes.
Okay, thank you.
Any other questions? Yes, please.
Is he going to be in the same room?
Same exact procedure as last time. Same room, same timing. Come between 9 and 10. Plan to spend. You have 90 minutes.
Is the breakdown the same of like written versus multiple choice, or is it more choice?
I think it's no. This one is more like half and half. There's more free response on this one. The last one was mostly multiple choice. This is mostly, or not mostly, but there's more free response on this one. But there's definitely a lot of multiple choice. Other questions? Okay. I hope I've hit everything. Let's. We got one more topic to cover. Oh, let's do this before we do the new topic. Let's summarize these techniques. So you have to have a good organizational structure in your mind about these. Because when you come to the exam, there's this whole aspect of identification, right? So in the web work, mostly you kind of knew which technique it was going to be for the most part. Not always, but tried to mix it up a little bit. But when you come to the exam, you need to be confident about identification. So let's talk just through these. The first thing we did was, and this is always the first one you look for, undoing the chain rule, right? Undoing the chain rule is always what you look for first. And so you're looking for what? This, or kind of this in disguise. Sometimes it doesn't follow, it doesn't look exactly like that form, but it still is kind of that form, right? So you're looking for this, or this kind of in disguise. What's the key? The key is you have a composite function, and you have the derivative of the interior on that composite. So here's our composite function. And then you also have the derivative of the interior of that composite function. That's the general idea. And which do you focus on to do it? Exhibit A or Exhibit B? A. Remember, and what we do is, your first attempt is antiderivative of the exterior function. Because we're trying to get G of F, right? We're trying to get G of F out of that. That's undoing the chain rule, okay? This is your first line of defense every time. This is your first thing you look for. Don't go on to other techniques until you for sure have ruled this out. Okay, then we talked about undoing the product rule. And we talked about 5 common forms. I'm not going to write them out again, but 5 common forms. Some power of x times a sine or cosine. Some power of x times e to the x. Natural log. Some power of x times natural log. And then the inverse trig functions. Okay? And we've written that down before. So you're always on the lookout for those 5 common forms. If you have one of those 5 common forms, then you know you've got undoing the product rule. Now, it sometimes works on other things that are not the common forms, but just beware. Okay, it could be a mess, but it might work, but it could not be the most optimal way to do it. Okay, so just if it's not one of the common forms, just use this with great hesitancy. Okay, and abort if it's not looking good. If it's blowing up on you. Okay. All right, partial fractions and long division, right? So what were the two criteria for partial fractions? So partial fractions is where we have a rational function, right? A rational function, which is one polynomial over another. And there were two criteria that made it ready for partial fractions. First is degree of the denominator is greater, or degree of the numerator is less. Other criteria was? Denominator has to factor, and it's at least two factors. If you've got both of those criteria, you can do partial fractions. Remember, long division is for when your numerator degree is greater than or equal to the denominator. Then you use long division first. And then when you do long division, then sometimes that remainder over divisor then is a partial fractions problem, right? You do the long division, that last fraction that you get is either easy or then requires partial fractions. Okay, next, trig identities. Okay, what was the deal with this? So you're changing the form using trig identities to get something easy, or staging for undoing the chain rule. That's what these are about. You just got done doing those. And then we have the new technique today, which is called change of variables, or u-substitution. Okay, change of variables or u-substitution. So as you're studying, what I recommend is make a more detailed kind of cheat sheet like this, right? So when you're coming to these practice problems, you can just look through your outline and practice identifying which of these is going to apply. You need that practice of identification so that you're using the right tool to try to work on it. Now, you won't have the cheat sheet at the test, but then hopefully by the time you get to the test, you have that thing that structure, memorized, and you can just access it mentally. Questions on the overview of these? Okay, so let's look at a problem here. Something new. Yeah, please. Yeah, go ahead.
Do you have to memorize the trig identities?
No, remember, so the trig identities is on the front page. Well, kind of. I'll meet you halfway. The front page, before you start the test, you fill them all out, and then I'll give you a bonus point. And then for the test, you'll have that as a reference. So I gave you on the exam prep, I gave you the sheet that's totally solved, and then I gave you a blank sheet to practice. So yeah, so you'll be filling those out on the front page, and for a bonus point, and then after that, you don't have to kind of memorize it. You don't have to be stressed during the test that you don't remember something. First question we ask. What's the first question we ask? Is it undoing chain rule? Is it undoing chain rule? Right? So we're looking for f prime g, g prime f, and f prime, right? Is it? No. Is it a common form of the product rule? Definitely not, right? Definitely not a common form of the product rule. It's not trig. Is it partial fractions? Okay, some are saying yes. So it sure doesn't look like a rational function, but it actually is. It's kind of a rational function here in disguise. So how can we see what rational function we're dealing with? What we can do is, what we can see is kind of like down here is like, do you see that this is something squared and something to the first and a constant? So this is kind of like a polynomial if what? It's like a polynomial of e to the x. Do you see that? It's like instead of a polynomial of x, it's a polynomial of e to the x. So let's change the variable. So we say u equals e to the x. So now we need to using u equals e to the x, we have to take care of everything that we need here. So if u equals e to the x, then what's the rate of change of e to the x? What's the rate of change of e to the x? And what's our, so if a rate of change is e to the x, what's our meaning for that? Given any what? Given any change in x, the change in u is that rate times the change in x. So is that a fair statement? Is du equal e to the x dx? As a rate, that's thinking of e to the x now as the rate of change of e to the x. Okay. Okay, so then, so we need to do as much math as we need to do here to get this whole thing in terms of u. Okay, and the reason that I did this was now we have this dx here, so we can take care of this dx. So let's just start here. Let's just do the denominator first. If u is e to the x, what's e to the 2x? U squared. And what's 3e to the x? 3u. Oh, so now it looks a little more friendly, right? And what was e to the 2x again, our numerator? U squared. So the question is, what is dx? Right? So what is dx? You're not always just going to replace it with du, because it's not. What is dx? Dx is du over e to the x, right? If I solve for dx. But what is e to the x? What do we say e to the x is? That's just u. So dx is du over u. So what am I doing? I'm changing the variable, the whole thing, the rate function and the dx, changing it from the variable x to the variable u, and that's all based on me deciding that u is going to equal e to the x. That means that du equals e to the x dx, which means that dx is du over u, and so then I substitute all those things in to change it from an x expression to a u expression. Okay, now notice, can we simplify that at all? Do you see, we got u squared, this is all together, over u, which means just a single u in the top, right? What if I didn't have this u squared here? What would happen to this u? It would just link up here in the denominator, right? It would just still be in the denominator. So just follow all the rules of algebra and arithmetic. Don't think that every example is going to be just like this one. You get to follow the correct algebraic rules and arithmetic. In this case, in this problem, u squared and u gives us a simplification to u in the numerator. But if that couldn't happen, then this u then links up with this. And we know we have partial fractions, so we don't want to distribute it, right? We want to factor the bottom. We want to leave it factored out. Okay, but in our case, it's gone. The u is gone. Okay, so now, so some of you are saying, yes, it's partial fractions. So is it partial fractions? Two requirements. Rational function with degree of the numerator is less, and so we need that to factor. If that doesn't factor, we can't use partial fractions, does it? It's easy, right? Super easy. And now we've got a problem that we know how to do, right? Partial fractions. I'm going to do it fast. So u plus 2 is linear, so we need a constant in the top. U plus 1 is linear, constant. So our numerator, when I add these fractions, my numerator will be a, so I'm going to do u plus 1 over u plus 1, right? In this one, it's going to be au plus a. And then I'm going to do u plus 2 over u plus 2 here. So it's going to be bu plus 2b. And what does that equal? U. We need it to be the original numerator. that means that a plus b equals 1, the coefficient of u. A plus 2b equals 0. There's no constant term. Subtract. Negative b equals 1. B equals negative 1. A equals 2. Check it. Works. Okay, so we can rewrite this as now, then, what? Negative 1 is b, so it's over u plus 1. A is 2, so plus 2 over u plus 2. So the whole point of this change of variables is we're getting it into a form that we can actually do the antiderivative, right? So all this was about getting to this partial fractions and then getting to here so I can actually do the antiderivative. So when I do the antiderivative, I'm still going to be in the variable u. That's the point. That's why I'm in u, so I can do the antiderivative. So what is it? Negative ln u plus 1 plus 2 ln u plus 2. Okay, with no limits of integration, we're talking about what? All accumulation functions that have the original rate function. So plus c. Am I done? No, because this problem was a problem of x, not u. So now, after we do the antiderivative, we change it back to x. So the whole point of changing the variables was to get to do the antiderivative in this new variable, and actually get a closed form in the new variable, and then we can switch it back. So it'll be negative ln of u is e to the x. That's what we said at the beginning. Done. How can I check my answer? If I take the derivative of this and do some, I should be able to, I'll get 2 fractions. Add those fractions, I should get that thing right there. I'm not going to take the time to do it, but so as you're studying, this is always the best way to check your answer. Take the derivative. And because our focus on this has been doing antiderivatives in the perspective of derivatives, every time you take a derivative, it's helping you with your antiderivatives, right? It's because we're basing all this stuff on a good knowledge of derivatives, not just a whole new set of rules, right? Okay, now, so if this were a definite integral, say we wanted to go from 1 to 8. Suppose this was 1 to 8. We have 2 options here. We could just do the whole problem and then come to this and evaluate it at 8. So now I want the net change, right? I want the net change starting from x equals 1 to x equals 8. So I could come to my closed form, evaluate it at 8, evaluate it at 1, and then do what? Subtract, right? I could do that. Or I have another option. So I could do that. So I could do what? ln of, I'm not going to write all that out. That's too long. The other option is I could find what u is when x equals 1. So when x equals 1, what is u? E, that's right, e to the first, or e. And when x equals 8, e to the 8th. So why did I do that? Because I could just get my antiderivative in terms of u, right? And now I know what those... what the corresponding u's are. So then I could evaluate, or I could evaluate that at the corresponding u value to 1 and the corresponding u value to 8, and then be done. I'll get the same thing. Does that make sense? So I could take these limits, e to the first to e to the 8th, and so what I'm saying is, if you have a definite integral, you don't have to switch back to the original variable. You can just switch your limits into the new variable and then finish that way. You see? Or I can go back to the original limits and evaluate those in the function changed back to the x variable. Okay, questions on this example? Anybody have a question? Can I erase? Okay, another example. That's a cube root. X times the cube root of x minus 8. First question. Is it undoing the chain rule? What small change to this would make it actually be undoing the chain rule? What squared? Under the radical. So you should thinking, if that under the radical was squared right there, now I've got undoing the chain rule. Do you see it? Or you should have thought that before we said it. So if there was a square there, undoing the chain rule. But there's no square there, right? This doesn't matter. These powers don't work out for undoing the chain rule. This x to the first and x to the first. Okay, is it undoing the product rule? Maybe. It might work. It might work, but it's not one of the common forms. Okay? Is it partial fractions? Definitely not. There's nothing to do with the rational function. Okay, it's not trig. So I think maybe, so it could be undoing the product rule, or we could try change of variables. What might help us here? U equals what? X minus 8, and we're going to see why that helps. So we'll do x minus 8. Then, what's the rate of change of x minus 8? 1. So 1 means, given any change in x, the change in u is 1 times the change in x. So du just in this case, du just equals dx. That's nice, but it's not always the case, right? So in this particular problem, it does. Okay, so we've got x minus 8, we've got dx. We need what x is. What is x going to equal? See that if u is x minus 8, then x is u plus 8. And now we got it. So x is u plus 8. X minus 8 is u. Dx is?
You said that x was u minus 8.
You add 8 to both sides, right?
Right. Oh, okay.
Yep, x equals u plus 8. Did it help? Is this progress? Why is this progress? Because this is the same as what? So if we write it this way, I mean this help. U plus 8 times u to the 1/3. What can we do with that? Yeah, this is just, so it's just u to the 1/3, and so because this is just u, it's just a sum of terms, we can distribute that now. We can't distribute x into underneath a cube root. It doesn't work. But now that this is u plus 8 just to the first power, we can distribute a monomial into that. So what do we get? U to the first times u to the 1/3, u to the 4/3 plus 8 u to the 1/3. Easy, power rule, right? So this would be u to the 7/3, 3/7. Add 1, right? U to the 3/4 times 8. Is that 6? Let me just write that out. Okay, and then are we done? 3/7 times u is x minus 8 to the 7/3 plus 6 times x minus 8 to the 4/3. Let's see. So maybe undoing the product rule would work, but this is definitely easier. This is definitely less stressful. Yeah, so maybe when you're contemplating, you have something that's not the common form of undoing the product rule, but you're kind of tempted to try it. Then maybe you have that triggers you to think maybe this is a u-substitution. So maybe if you're tempted to use undoing the product rule, but it's not one of those common forms, then something raises a flag to think about possibly a substitution, change of variables. Questions on this example? Okay, your turn, and I'll take attendance. Lots of work there. Everyone's working on these. Ben can walk around to help. You're either making progress or you're getting assistance. Yeah, they did long.
Oh,
This. This first two. Okay, I got this. I did the setup for the first two. Look at it. See if you how'd you did.
Sometimes, like, I feel like it's long. Yeah.
Okay, questions on the first two, the setup that I did. Yes, please.
I'm just curious how you got x minus 1 equals 2 minus 3.
I showed that right through here. So I first got 1/2 x was u minus 1. And then I got x was 2u minus 2. And then if I subtract 1 from both sides, I get 2u minus 3. So it's this progression right through there. I just solve this for x and then subtract 1. Just solve this for x and you get 2u minus 2. Subtract 1, you get 2u minus 3. Other questions? Then from there, in this first one, straightest line I've drawn all day. 2u minus 3 squared over the square root of u times 2 du. How are you going to do that? That's what you get when you switch it into the variable u. What are we going to do now? Did it help? Or did we make progress? Because? Kind of. So we're going to FOIL this out. We're going to FOIL this out. And when you have multiple terms over just a single term, then we could split it into 3 different fractions. The first over radical u, the second term over radical u, and the plus 9 over radical u. And then you just have 3 easy power rules. Do you see it? You FOIL this out. Take each term of the numerator divided by this radical u as 3 separate fractions. Use your rules of exponents. And then you've got just kind of like a polynomial. You're going to do I need to talk about that one anymore? Okay, this one, same thing. Now I'm going to what? FOIL out the u minus 4 squared. And then distribute the u to the 19th in. And then I've got a polynomial. Easy. So I'll leave those up to you to finish. Any questions about those first two? Yeah.
You don't have to write right now, but just at some point, the final answer is just
How can you check your final answer? Yeah, it's okay. Yeah, so you can take the derivative, but if you after class, I'll work it through if you want to look at it after class. Okay, this one. What are we going to do in this one? Okay, so this is not undoing chain because the derivative of cosine squared is not sine, right? So that kind of looks like it is. The derivative of cosine is sine. So if it was cosine x plus 7, sine over cosine plus 7, that would be undoing chain. But because it's cosine squared, the derivative of cosine squared is 2 cosine x times negative sine x. That's not this. So instead we could do u equals cosine x. Then du equals negative sine x dx. Now look at what just happened. So sometimes this happens. Notice the original integral. Notice something? Here's sine x times dx. What do I have? Sine x times dx. So rather than figure out what dx is and figure out what sine x is, I can just recognize that this whole thing right there is it's what I have. So then this sine x dx equals what? Negative du. Do you see that? So that whole thing, that whole sine x times dx is just negative du. Then over u squared plus 7. Okay, now what? You've actually come across this before. This is not, so it's not undoing the chain rule. It's not partial fractions because that doesn't factor. Okay? What you have to recognize is this is really close to 1 over u squared plus 1. If we had 1 over u squared plus 1, what would the antiderivative be? You just have to know this. You got to recognize these things. Arctangent. Make sure you know the derivative of arctangent, the derivative of arcsine, and the derivative of arccosine. So you're on the lookout for those. You got to know those. This is really close to derivative of arctangent, but we need a 1 there. So what can we do? We can take 1/7 over 1/7 to make that 7 a 1. So we'll have negative 1/7 over u squared over 7 plus 1 du. And then I can change this to, I need it all something squared. So u squared over 7 is what squared? U over square root of 7 squared. Now I've got arctangent. Arctangent of what? Arctangent of u over square root of 7. I also have negative 1/7. I also need a square root of 7. Because when I take the derivative of that by the chain rule, I'm going to have times 1 over radical 7, which I don't have in there. So I need to get rid of that. So there. So that's our antiderivative with respect to u. And then u is cosine x. So I'm going to put cosine x right there for the final answer, plus c. Okay, I'll leave it up if you want to come down and ask me on your way out. Study and get your questions answered. See you in the art building Friday.